Today we're going to talk about turning complex geometry into primitives for analysis. We'll call this primification. So the first question really comes from, how do we turn this complex geometry into this simpler geometry? Well, the process isn't very hard, but it can be a little complex. The first step is to find all of these inflection points, which is points that we know the geometry is changing. We can then turn these into points and then use those points to generate a 3D sketch. Step 1. Finding connecting points and mapping them out. So one of the main problems when we're trying to use this primification method is finding the points where the lines of force connect. As you can see here, I've already lined up a number of these points and generated a sketch. So we'll go through this just to show you how I generated this piece. I find it useful to start from the bottom on most of my pieces. So here we go to the base, and the really important thing is to give yourself a good base to start from. And this leads into one of the biggest parts of how to do this method, is to use something like this section analysis tool. This allows us to cut the part where we'd like and then view in profile the circumference of a lot of the geometry here. So the main thrust of this whole workflow is to get in here and find the center point of these different pieces at the points that we're trying to find. So here we've set the very bottom piece, as you can see, and we're trying to find the lines of force that pass all the way right there. So you can see it basically consists of putting down a circle and then moving the camera until you have generated about the center of this semicircular geometry. And as you can see, we'll just go through and we'll add all of these for these 4 bases. At this point in the process, it's not too important to be accurate. All of these will be adjusted later. Once we get the entire skeletonized structure set up, we can adjust everything based on the geometry. So as you can see here, we have the base set up, and this is a good place to start. Now we also have a number of bolt holes here, and those are really important to model, as those are where the forces typically generate from. And since we're basically creating a 3-dimensional sketch of the lines of force as it moves through the part, we need to model these correctly. So one of the best ways that I've found to do it is to use the what's called the projection tool, and this lets you project existing geometry onto your sketch plane. This is really useful in allowing us to just really quickly find the centers of lines or the center points of holes. And so here we can go ahead and model the center of that hole, and later we can connect it to the line of force running up through the leg. Now that we've generated a couple of these points to attach with our 3D sketch, we need to start going through the geometry and finding places where there's inflection. So for the most part, you can see these legs, they pass straight up. There's no real question as to whether they bend or not. They get a little thicker, but they don't move. Now you can see as we move up here, they go straight, and then at a certain point, we lift it up and they become straight. So you can see here, there's the point where they have moved and become straight. So by dragging this up and down, we're able to actually see where these inflection points are a lot easier. So the point here would be to now find that relative point where that inflection change happens, and then set down a plane and develop a sketch and put down your points. It's the same as we did before, and it's just iterative as we go up. Like I said, the process isn't very difficult. It can get complex though, because generating these individual points really comes from having a feel, as you can see here. Because once you find that point and you're happy with it, and you set down your plane and you create your sketch, then you can come in and you can see pretty clearly, in my opinion, where the center of these actually lie. So here you can see I've just set 2, and this is a good time to talk about these sorts of flats versus cylinders. Like the legs are cylindrical and they're pretty easy to find, but this whole central structure here is created with a triangular solid. So for the most part, I've found that you can just model the outside, and you can see it's very easy to see where those round outer supports go, and the rest of it is material that mostly hasn't been taken out. Sometimes it is definitely something that's needed for support, but I find you'll find pretty quickly when you start to do analysis of that, if that's the case. So you can see here we have a point where we have 3 supporting structures that all meet at a triple node. Now these look intimidating at first, but you can see here in the profile it's very clear where these lie. Now on the inner one we do have what looks like 2 inflection points, so I'm only marking the outer 2 here because I'm mostly concerned about the outer support structure here as opposed to that inner structure. That inner structure we can begin to build out by using a section view from a different perspective, and that'll allow us to see it a lot easier. The final point here is to move up and find that final bolt point. And again, it's important to get these in there because this is where the lines of force will originate or end. So in our case, this is a load, and this combined with the bottom one create the lines that actually permeate through the structure. And again, just like before, we'll go in and we'll use the project feature and we'll construct and find the center point for this bolt hole. Now that we have these geometries that represent the outer structure, now we can start to focus a bit on this middle structure. Now it seems a little bit more complex because everything is at an angle, it radiates from the middle. How do we get it to connect to the sides? By using the section view again, as we did before, it's the same process. There's no real difference between it. Even though these are all at an angle, the points that we're trying to find are points, and so it doesn't matter what angle the projected surface that they're on lies on, it's still a point. So the point connections can come from any angle when we do our 3D sketch. And as you can see here, it's just a plane in the middle, and then we do the same process to begin to build out these different connections. And as you move this in and out, as you can see, it becomes a lot more obvious where the central lines in each one of these support structures is. And again, you go in and you line up your central support structure, then you drop down your circle, and that lets you locate the point that you were trying to place. So the question then becomes, how do we take care of these supports that aren't straight or that don't lie on a plane that's easy to define? So it's the same process again, nothing deviates, where we take our section view and we can slide it out to find where those connections occur. Now we're really looking to connect the lines of force, which means we want to connect this line to the center of the side support line. So if we put a plane that's relatively through the center of that side support, we can adjust our section view so that we can see about where that would lie. And this is a good time again to reiterate that at this stage, exact accuracy in placement of the point isn't very important because we will be adjusting that later in a later step. And you can see here we are placed about in the middle of this support section, but we're still obscured from seeing our support. So we can just go ahead and pull our section view back and line up our point according to the center of this support. And to micro adjust, we can grab the construction circle that we've used. I do like to use large circles when I'm doing this method because they tend to extend past the geometry that we're working with and give us something easy to grab onto. So now that we've done this central support, what about this angle up here? So these are all meeting at the central knot. So we want to go ahead and provide an anchor point to put our 3D sketch at that location. So we'll create a sketch that's relatively on the line of force on that central piece, and then we'll lay down another piece with the same method, looking down the shaft that we're trying to find the center for. And again, don't worry about this being at an odd angle. We are dealing with points here, so the points themselves don't care about the orientation of the plane. And from here, it's just basic iteration. As you can see, all of the different steps that we've taken have ultimately been the same step, where you determine the support structure that you're trying to find the end point and beginning point for. You lay down a plane where you want that point to lie, and then you go ahead and just put down a circle or a point, completely up to you. Like I said, I prefer to use circles because it gives me something to grab onto and it's just a nice round object. So one of the other problems comes in Much of this geometry isn't very clear in where the lines of force might actually lie. If it's a cylindrical support, then that's easy to determine, but what about these other sections that seem to be made of just an organic shape? Well, in this case, again, as before, we use our section view. When we cut these into profile, it's often pretty obvious where the lines of force would lie. As you can see here, something that looked like an amorphous blob, when we cut it into sections, we can clearly see 3 different rounds here. And as I was saying earlier, you can see that section is actually composed of an inflection point very close to this connection point. So we'll have to model that later. But for now, we'll drop this point, and then we can go ahead and move on to additional points. Now, I won't sit here and model every single individual point for you. As you can see, the process is very iterative. It's not very complicated. It can just be complex. The last thing that you'll have to really consider is, in order to drop a lot of these 3D sketches onto these connection points, we will need to create points for them. So as you can see where I'm turning on all the different sketches that were necessary to produce this 3D sketch, you can see that some of them actually just have lines. They don't consist of any circles. So this is done because we can go into a sketch and then use an existing line to project onto our sketch point, and then we can connect the line that we'd like onto that projection point. This allows us to place points on 3D sketches that we wouldn't otherwise be able to have access to. For example, here the purple lines are all projections, and those were created from the connection points that we made in previous sketches. So now that we have all of our points in place, we can move on and begin to actually generate the 3D sketch in step 2, which is generating the 3D sketch. Now this is the easiest part of this entire workflow. We've already done the bulk of the work in setting up all of these points, as you can see. Really at this point, it's just playing connect the dots. Now, Fusion 360 does seem to have some particular things that it likes to do when you put this into 3D sketch mode. It means that once you lay down a point, you tend to not be able to move it. This is partly why we've created all of these nodes. And that'll get into in a little bit, but for now, we're just going to go ahead and go up to the line tool after turning on our 3D sketch and just start connecting the actual points. That's really about all there is to it at this point. So we'll start at the bottom, and then we'll go ahead and we'll follow the lines of force up through the points that we made, trying to mimic what we would have done if we were, say, designing this with a pipe structure. So here we've gone up, gone through, you can see the different turns that we've made going up to the bolt, and then we'll come back down along the back leg. And then we can turn off our line tool, and then we'll just do this again on the other side. Now, as I said, there's really not much more to it than this for the 3D sketch tool. We've already done the vast majority of work in setting the points, and now just go through and connect the different lines of force. Like here is the other bolt hole, so we'll just connect it directly over there. This is why we created the different connections along that line earlier too, because that way we can connect to our lines of force very easily. So in here we'll do the other side, and you can see it's the same method. It doesn't really matter which part of the design you're on. We'll connect all of these points, and later we can go through and start to think about the mechanics of the lines of force and start to add connections between those points that maybe weren't as obvious. Say up near the top where we had some thick material, we might want to connect some more of those lines of force just to represent the fact that this is a solid structure and the lines of force are radiating through it. So here we'll do the center structure to the sides, and here especially is where it shows why we spent some extra time putting in lines and points, because we end up with this very complicated structure. And as you can see from the top, we've gone through and we've lined up as many of the lines of force as we can. But This in and of itself is a pretty complicated design. So what if you decide that it's not correct? You can look through and look at this geometry and make sure that the lines are about where you want. But the beauty with this method is we can just go into any one of the sketches that we initially defined and move those points. And as you can see, the 3D sketch will update. This is why at the initial point we weren't really concerned about exact accuracy. We just needed to get around where the centers were, because at this point we can come in and we can adjust and fine tune and make sure that our lines of force actually align with the geometry that we had actually established from the beginning. And this is where this method really begins to shine, because you can see the reason we've spent so much time defining these particular points for our connections is because then we can adjust them in real time to make sure that they align precisely. But this is still really complicated, and is that necessarily useful? Well, for analysis it might not be. As you can see here, we just went in and started to adjust things so that they may be lined up a little bit more cleanly in something that might be considered a bit more of a human-centric design. And you can see upon laying these out that it's not only simplified, but we've actually, say, straightened out that central member, whereas it was slightly bent. And so this is where it starts to become a little bit on the designer or the engineer as to decide what the optimal load path is. And from here it's just as simple as opening up the export command, going down and saving this particular sketch as a DXF. Just make sure you have the sketch selected on the left, and that's really about all there is to it, to exporting this. And step 3, Primification. So ideally you want to bring this DXF that you saved back into a CAD program. So here we're using Fusion 360. An important thing to note if you are using Fusion 360 is you'll want to turn on your design history. And that way you're capturing that as you work. And that's just a nice cleaner workflow. So in order to get this into primitives, which is why we call it primification, we're going to use the pipe tool here. And as you can see, when you do that, this gives you a number of parameters. You can set the diameter, you can set the shape, you can set the tangencies, you can set whether or not it's hollow. So here we're just going to do solid pipes, and we're going to go ahead and make sure you click on the correct things. We turned off tangencies because a couple of these lines are lines of force that lead to the center of our bolt, so we don't necessarily want to add anything there. The other important thing to note when you're using this tool is you do want to try to create the pipes in a way that they would normally flow. So here we know that these pipes would flow up and around the side. This gives them more realistic connections as you're going. And you can see with just that simple motion, we have one side of the support. And from here, it's just continuing this. So we want to make sure that we continue and do pipes that are on the same line. So we're going to go ahead and grab all of these. If we try to do lines that are off this line, it's not going to allow it. So we're going to have to do several pipe maneuvers, which is good because that means if you want to adjust things later, you have multiple things to adjust and you're not tied to one command that has all of them going. And again, we're just going to keep going from here. So we'll grab the other side next, grab our pipe tool, and we'll just race right up and down this side structure. It's very simple. And again, we can go in and we have these connection points that we did in between these supports, so we can add some connections there once we've added this central structure. And as you can see, as we're building this out, it's creating the connections between them, and these are very clean. This is why we're using the pipe tool instead of trying to, say, extrude these things. We also don't need to worry about planes or anything like that. This will just produce a pipe along those lines. And you can see here we have that little angle right there. No need to worry about connecting. You can just use the pipe tool, select that central piece right there, and it will go ahead and build out the connections between all of those connecting pipes. It doesn't really matter what order you do it in. If you do those first, if you do them second, it'll still produce the same geometry. So now we mostly have this structure complete. As you can see, it's made of pipes. So what if you don't like the thickness? Well, it's as simple as picking the part that you want to change, going to the command, and coming up here, changing the thickness. It's really not much more to that. And as you can see, now we have the basis of the structure. So I've gone ahead and loaded the completed model, as you can see here. Now, this isn't finished. As you can see, we do have no connection points, we have weird points at the top. So at this point you would just go in and clean it up the same way you would a normal model. As you can see, I've already done it. So I'll let it play here so you can see it as we kind of go over this. So the method in and of itself is very simple. It's to create a series of planes along the points that you know connections exist, drop down a point that'll later then be connected in a series of connect the dots in a 3D plane, a 3D sketch, and once you have your 3D sketch, you just generate primitives from it. Not very complicated, but effective. So now you might ask, what was the point of all this? Does it work? So we've done FEA analysis on the different parts, and the numbers all agreed. The only discrepancies lie from the fact that there's less mass in the part that we produced, and with tuning of the diameters as well as the node locations, we can find almost complete agreement between the two models, which shows that it does indeed work. Moreover, the resulting primitive and the resulting 3D sketch that we've produced can be sent over to any analysis software such as Nastrans or from ANSYS that's considered industry standard or professional. And that's the real strength of this. You can take these and you can do, say, heat analysis on a very complex object in a very short amount of time using this method. And that completes our talk on primification. Thank you for your time, and if you have any comments or questions or suggestions, feel free to leave them in the comment section and I will respond. Thank you.